In today's data-driven world, organizations are increasingly turning to data science to extract meaningful insights from the vast amounts of information generated daily. The global data science market is projected to reach $273 billion by 2005, highlighting its growing importance across industries. An astonishing 97 zettabytes of data were created in 2002 alone, showcasing the exponential growth in data generation and the opportunities it presents for businesses, researchers, and society to harness information in powerful new ways. Data science is an interdisciplinary field that combines mathematics, statistics, specialized programming, advanced analytics, artificial intelligence, and machine learning to uncover hidden insights within an organization's data. At its core, data science is about using scientific methods, algorithms, and systems to extract knowledge and insights from structured and unstructured data. It transforms raw data into business value by identifying patterns, predicting outcomes, and recommending actions that drive strategic decision-making. The journey of data science began in the 1960s and 1970s, with early foundations in statistics and computational methods. Although the term data science didn't exist yet, the groundwork for statistical computing was being laid. In the 1990s, the growth of data warehousing, business intelligence, and early data mining techniques marked a significant evolution as organizations sought to leverage growing digital data. In 2001, William S. Cleveland formally coined the term data science in his paper, advocating for its expansion beyond traditional statistics. Today, the explosion of big data technologies, machine learning advancements, and the emergence of data science as a distinct professional discipline continue to shape its evolution. Data science is transforming industries across the globe. In entertainment, platforms like Netflix use advanced data science to analyze viewing patterns and preferences, keeping subscribers engaged with personalized content. In healthcare, data science played a crucial role during the COVID-19 pandemic, creating sophisticated prediction models that helped hospitals with resource allocation and patient care. In retail, major retailers use data science to optimize inventory, personalize marketing, and predict consumer behavior, enhancing customer satisfaction and digital shopping experiences. The data science workflow is a systematic process that begins with data collection from various sources, including databases, APIs, sensors, and web scraping. Data preparation involves cleaning, transforming, and ensuring data quality through techniques like handling missing values and normalization. Analysis explores data through statistical methods and visualization to identify patterns and relationships. Modeling builds predictive or descriptive models using machine learning or statistical techniques. Finally, deployment implements models in production environments to drive decision-making and automate processes. Data science integrates multiple disciplines to transform raw information into valuable insights. Business intelligence provides actionable insights for decision-making, while machine learning offers algorithms that improve through experience. Statistics provide mathematical analysis of data relationships, and data engineering offers the infrastructure to collect and process data. Together, these components transform technical competencies into strategic decision-making across organizations. Data science involves various key roles that contribute to its success. The data scientist is a multidisciplinary expert who combines statistics, programming, and domain knowledge to extract insights from data. The data engineer builds and maintains data pipelines, ensuring that raw data is properly collected, transformed, and stored. The business analyst translates business needs into data solutions, identifying requirements and creating visualizations that help stakeholders understand complex data insights. The machine learning engineer focuses on implementing and scaling machine learning algorithms, optimizing models for production environments. The data science Venn diagram illustrates the intersection of programming skills, math and statistics, domain knowledge, and data science itself. Programming skills include proficiency in languages like Python, R, and SQL, essential for algorithm implementation and data manipulation. Math and statistics provide the understanding of statistical concepts and methods, crucial for probability theory and experimental design. Domain knowledge encompasses industry-specific expertise, business processes, and subject matter expertise. Data science is the sweet spot where all these areas converge, enabling end-to-end problem-solving and business value creation. Programming languages are the backbone of data science applications. Python leads with an 87% industry adoption rate in 2023, favored for its versatility and ease of use across the data science workflow. SQL is used by 63% for database queries and data manipulation, while R is popular in academic and research environments with a 42% adoption rate. Julia, with an 11% adoption rate, is growing in popularity for high-performance numerical computation. Each language offers unique strengths that cater to different aspects of data science. Data science relies heavily on libraries and frameworks to streamline processes and enhance capabilities. Pandas is a powerful data manipulation library, providing data frames for intuitive handling of structured data. Scikit-learn offers simple and efficient tools for data analysis, including regression, classification, and dimensionality reduction. Matplotlib is essential for creating static, animated, and interactive visualizations in Python. TensorFlow and PyTorch are deep learning frameworks that support both research and production deployment, enabling complex neural networks and machine learning models. Data acquisition is the crucial first step in any data science project. Organizations typically begin with accessing their structured databases, which contain organized information from internal systems. APIs and web services provide programmatic data access, while web scraping extracts information from websites. IoT and sensors expand data streams by collecting real-time data from the physical world, offering new possibilities for predictive maintenance, environmental monitoring, and response systems. These methods ensure comprehensive data collection for analysis. Data science deals with various types of data, each with unique characteristics. Structured data is highly organized and fits neatly into relational databases, representing about 20% of all data. Semi-structured data doesn't conform to rigid formats, but has some organizational properties like JSON and XML files. Unstructured data lacks predefined organization, including text documents, images, audio, and video files, representing approximately 80% of all data. Understanding these types is crucial for effective data analysis and processing. Data cleaning is a critical step in the data science process, as data scientists spend an astonishing 80% of their project time on this task. It involves handling missing values, removing duplicates, correcting errors, and addressing outliers to ensure data quality. Effective data cleaning techniques help build robust models that yield accurate predictions, avoiding the pitfalls of garbage in, garbage out. This step is essential for making informed decisions based on reliable data. Exploratory data analysis, EDA, is a critical preliminary step that helps data scientists understand their data before building models. Univariate analysis examines individual variables through summary statistics and visualizations, revealing central tendencies and outliers. Bivariate analysis investigates relationships between pairs of variables using scatter plots and contingency tables, identifying potential associations. Multivariate analysis explores multiple variables simultaneously, uncovering complex patterns and structures. Time series analysis examines temporal patterns, revealing trends and cycles over time. EDA generates hypotheses and guides subsequent analytical approaches. Descriptive statistics provide a quantitative summary of a dataset's main characteristics, including measures of central tendency like mean, median, and mode, and measures of dispersion like standard deviation and range. These statistics help data scientists quickly grasp the distribution of their data and identify potential anomalies. For instance, a significant difference between mean and median might indicate skewed distribution, while a large standard deviation suggests high variability in the dataset. Understanding these metrics is crucial for effective data analysis. Data visualization techniques transform complex data into intuitive visual representations that highlight patterns, trends, and outliers. Bar charts excel at comparing categorical data, while scatter plots reveal relationships between variables. Heat maps display intensity variations across multiple dimensions, and line charts track changes over time. Beyond individual charts, interactive dashboards integrate multiple visualizations to provide comprehensive views of data from different angles, supporting data-driven storytelling and decision-making. Feature engineering is both an art and science, making the difference between mediocre and exceptional model performance. It involves selecting relevant variables by removing redundant or irrelevant features, converting existing features into more useful formats, creating new features from existing ones, and encoding features into numerical formats. Techniques like one-hot encoding, label encoding, and advanced embeddings are used for high cardinality variables. This process requires creativity, domain knowledge, and technical expertise to craft features that meaningfully represent the underlying patterns in the data. Dimensionality reduction techniques are essential for simplifying high-dimensional data into more manageable forms. Principal component analysis, PECA, transforms data into a new coordinate system, highlighting the greatest variance along principal components. TSNE is popular for visualizing complex datasets in 2 or 3 dimensions, particularly effective in clustering applications. Autoencoders compress data into a latent space, capturing essential features while filtering out noise. These techniques are crucial for reducing complexity and improving the efficiency of data analysis. Model selection is a critical decision in data science, influenced by the nature of the problem, data characteristics, and desired outcomes. Regression models predict continuous numerical values, while classification models predict categorical class labels. Time series models analyze temporal patterns, and clustering models group similar data points. Selecting the appropriate model involves trade-offs between accuracy, interpretability, computational constraints, and the problem's context. This decision shapes the effectiveness of data-driven solutions. Supervised learning involves algorithms trained on labeled data to make predictions or classifications, requiring clear evaluation metrics. It's used in applications like credit scoring and fraud detection. Unsupervised learning identifies patterns in unlabeled data without explicit guidance, discovering inherent structures and relationships. It's exploratory in nature, used in customer segmentation and anomaly detection. Understanding the differences between these learning approaches is crucial for selecting the right method for specific data science tasks. Regression models are powerful tools for predicting numerical values by learning relationships between input features and target variables. They can be linear or more complex, capturing intricate patterns in data. Evaluating these models often involves metrics like R-squared and mean-squared error to assess their predictive power. Classification models help determine the probability of an observation belonging to a specific class. Logistic regression, decision trees, and random forests are popular methods, each with unique strengths. These models are crucial for tasks like fraud detection and spam filtering, as demonstrated in the email spam detection case study. Clustering methods group data into distinct clusters based on similarities. K-means, hierarchical clustering, and DB-Eigen are popular techniques, each offering unique advantages for organizing data. These methods are essential for discovering patterns and structures within complex datasets. Time series analysis focuses on data points collected sequentially over time, capturing trends and seasonal patterns. Techniques like ARIMA and Facebook's Profit are used for forecasting future values, helping businesses make informed decisions based on temporal data. Deep learning is a subset of machine learning that uses neural networks to model complex patterns in data. Key components include network architecture, activation functions, and training processes. Image recognition is a prominent application, revolutionizing fields like medical imaging and autonomous driving. Natural language processing, NLP, enables computers to understand and process human language. Techniques like text pre-processing, sentiment analysis, and language models are used to analyze and generate text. Chatbots and virtual assistants are practical applications, enhancing customer interactions. Model evaluation and validation are critical for assessing the performance of machine learning models. Techniques like confusion matrix, ROC curve, and cross-validation help ensure models are accurate and reliable, guiding improvements and optimizations. Overfitting and underfitting are common challenges in machine learning. Overfitting occurs when a model learns the training data too well, while underfitting happens when a model fails to capture the underlying pattern. The bias-variance trade-off is key to finding the right balance for model complexity. Hyperparameter tuning is essential for optimizing machine learning models. Techniques like grid search, random search, and Bayesian optimization help find the best model configurations. Automated tuning tools further streamline this process, enhancing model performance. Model deployment bridges the gap between experimental data science and real-world applications. It involves code packaging, infrastructure selection, API development, and monitoring implementation. This ensures models are effectively integrated into business processes. Working with big data involves processing large datasets using tools like Hadoop and Apache Spark. These technologies enable distributed computing, overcoming limitations of single machine processing and allowing for scalable data analysis. Cloud data platforms like Google, BigQuery, Amazon Redshift, and Snowflake offer scalable solutions for storing and analyzing large data sets. These platforms provide flexibility and power, enabling efficient data management and analysis. Data science and business intelligence are converging, offering advanced insights and predictions. Integration approaches combine traditional BI with data science capabilities, enhancing decision-making and strategic planning. A/B testing and experimentation are used to compare different versions of a variable to determine which performs better. This method relies on data-driven decisions, optimizing user experiences and increasing conversion rates. Data ethics and responsible AI. Focus on fairness, transparency, privacy, and accountability. These principles guide the development and deployment of AI systems, ensuring they are used ethically and responsibly. Data security and privacy are crucial for protecting sensitive information. Techniques like encryption, anonymization, and differential privacy help safeguard data while complying with regulatory standards. Collaboration in data science projects is facilitated by tools like version control systems, project management platforms, and collaborative environments. These tools enhance teamwork and streamline project workflows. Data science in finance is transforming the industry with applications like fraud prevention, algorithmic trading, risk assessment, and customer insights. These innovations improve accuracy and efficiency, driving better financial outcomes. Healthcare applications of data science include diagnostic assistance, personalized treatment, and operational optimization. These advancements improve patient care and streamline healthcare processes, enhancing overall efficiency. Retail and e-commerce are leveraging data science to enhance customer experiences and optimize operations. Techniques like inventory management and personalization are used to increase efficiency and drive sales. Manufacturing has embraced data science to revolutionize traditional production paradigms. At the foundation, advanced computer vision systems inspect products at speeds and accuracy levels impossible for human inspectors, reducing defect rates by up to 50% in some facilities. These systems analyze thousands of images per minute to identify even subtle defects. The most transformative application is predictive maintenance, which uses sensor data and machine learning to forecast equipment failures before they occur. By analyzing patterns in vibration, temperature, and other variables, these systems reduce unscheduled downtime by approximately 40% and extend machinery lifespan by 20-30%. This shift from reactive to predictive maintenance has generated billions in savings across the industrial sector. Data science is transforming government and policy through smart cities, crime analysis, population analytics, and economic forecasting. Smart cities utilize sensor networks and analytics to optimize traffic flow, reduce energy consumption, and improve public services. Cities like Barcelona and Singapore have implemented comprehensive IoT infrastructures that collect and analyze data from thousands of connected devices to enhance city management. Crime analysis systems identify high-risk areas and predictively police them, improving resource allocation. These tools analyze historical crime data alongside demographic, geographic, and temporal factors to forecast potential hotspots with increasing accuracy. Population analytics combine traditional surveys with modern data sources like satellite imagery and mobile phone data to provide robust population distribution and characteristics, supporting evidence-based policy development. Economic forecasting models predict economic trends by integrating traditional indicators with novel data sources like consumer sentiment from social media and real-time spending patterns from payment processors. These insights help governments develop targeted economic policies. The world of sports analytics has been revolutionized by data science, with groundbreaking approaches like the Moneyball revolution, player performance tracking, and strategic decision-making. The Oakland Athletics' pioneering use of statistical analysis to identify undervalued players transformed baseball and inspired data-driven approaches across sports. By focusing on overlooked metrics like on-base percentage rather than traditional statistics, the team built a competitive roster despite having one of the lowest payrolls in Major League Baseball. Player performance tracking systems now capture millions of data points during games and training sessions. Computer vision systems track player movements, analyze biomechanics, and provide personalized metrics like heart rate and exertion levels. These insights help teams optimize training regimens and reduce injury risks. Strategic decision-making models optimize game strategies and tactical decisions. In basketball, shot selection models analyze player tendencies, while soccer teams use data-driven approaches to enhance individual and team performance. These advanced models and approaches challenge traditional sports wisdom and continue to drive advancements for analytics-savvy organizations. Data science is increasingly being leveraged to address pressing social and environmental challenges. In disaster response, machine learning models analyze satellite imagery to rapidly assess damage after natural disasters, helping emergency services prioritize areas that need assistance. Disease prevention efforts use data to identify high-risk demographics and forecast disease spread, enabling targeted interventions. Wildlife conservation efforts utilize computer vision to track endangered species through camera trap images, while acoustic data analysis detects illegal logging and poaching in protected areas. Climate scientists employ sophisticated models to improve climate predictions and evaluate mitigation strategies, providing crucial information for policy decisions and adaptation planning. Poverty reduction initiatives use data to identify vulnerable populations and design effective interventions, ensuring resources are allocated efficiently. Recent breakthroughs in data science are pushing the boundaries of what is possible, with innovations like AlphaFold protein research, GPT-4 level language models, diffusion models for image generation, and reinforcement learning from human feedback. DeepMind's AlphaFold has revolutionized protein structure prediction, solving a 50-year-old challenge in biology. The deep learning system can predict a protein's 3D structure from its amino acid sequence with unprecedented accuracy, accelerating drug discovery and enhancing our understanding of disease mechanisms. GPT-4 level language models have achieved remarkable advancements in natural language processing, understanding, and generation. These systems can write coherent essays, summarize complex documents, translate languages, and even generate creative content from natural language descriptions, transforming human-computer interaction. Diffusion models for image synthesis have enabled the creation of stunningly realistic images from text descriptions. Models like DALL-E, Midjourney, and Stable Diffusion have demonstrated the potential for new applications and novel possibilities for design and visual communication. Reinforcement learning from human feedback is aligning AI systems with human preferences through techniques that incorporate human feedback into the learning process. This approach helps AI systems avoid harmful outputs, enhancing the safety of AI assistants while reducing harmful outputs. The retail sector has been transformed by data science applications that optimize operations and enhance customer experiences. Inventory management systems now incorporate machine learning to predict demand patterns with unprecedented accuracy, reducing stockouts by up to 30% while decreasing excess inventory costs by 25%. Personalization engines analyze browsing history, purchase patterns, and demographic information to create tailored shopping experiences. These systems increase average order value by 10 to 115% through relevant product recommendations. Perhaps most innovative is Amazon's patented predictive shipping model, which begins the fulfillment process before customers place orders based on predictive analytics, ensuring timely deliveries. Manufacturing has embraced data science to revolutionize traditional production paradigms. At the foundation, advanced computer vision systems inspect products at speeds and accuracy levels impossible for human inspectors, reducing defect rates by up to 90% in some facilities. These systems analyze thousands of images per minute to identify even subtle defects, ensuring quality control. The most transformative application is predictive maintenance, which uses sensor data and machine learning to forecast equipment failures before they occur. By analyzing patterns in vibration, temperature, and other variables, these systems reduce unscheduled downtime by approximately 40% and extend machinery lifespan by 20 to 25%. This shift from reactive to predictive maintenance has generated billions in savings across the industrial sector. Government and policy sectors are increasingly adopting data science to improve urban management and public safety. Smart cities utilize sensor networks and analytics to optimize traffic flow, reduce energy consumption, and improve public services. Cities like Barcelona and Singapore have implemented comprehensive IoT infrastructures that collect and analyze data from thousands of connected devices to enhance city management. Crime analysis systems identify high-risk areas and predictively police them, allowing for efficient resource allocation. These tools analyze historical crime data alongside demographic, geographic, and temporal factors to forecast potential hotspots with increasing accuracy. Population analytics combine traditional surveys with modern data sources like satellite imagery and mobile phone data to provide robust population distribution and characteristics, supporting evidence-based policy development. Economic forecasting models predict economic trends by integrating traditional indicators with novel data sources like consumer sentiment from social media and real-time spending patterns from payment processors. These insights help governments develop targeted economic policies. Sports analytics has transformed the way teams strategize and evaluate player performance. The Oakland Athletics' pioneering use of statistical analysis to identify undervalued players transformed baseball and inspired data-driven approaches across sports. By focusing on overlooked metrics like on-base percentage rather than traditional statistics, the team built a competitive roster despite having one of the lowest payrolls in Major League Baseball. Player performance tracking systems now capture millions of data points during games and training sessions. Computer vision systems track player movements, analyze biomechanics, and provide detailed insights into metrics like heart rate and exertion levels. These innovations help teams optimize training regimens and reduce injury risks. Strategic decision-making models optimize game strategies and tactical decisions. In basketball, shot selection models analyze player tendencies, while football teams use data-driven approaches to enhance play calling and formations. These advanced models and approaches challenge traditional sports wisdom and continue to drive competitive advantages for analytics-savvy organizations. Data science is increasingly being leveraged to address pressing social and environmental challenges. In disaster response, machine learning models analyze satellite imagery to rapidly assess damage after natural disasters, helping emergency services prioritize areas that need assistance. Disease prevention models use data to identify high-risk areas and predict disease spread, allowing for timely interventions. Wildlife conservation efforts utilize computer vision to track endangered species through camera trap images, while acoustic data analysis detects illegal logging and poaching activities. Climate science employs sophisticated models to improve climate predictions and evaluate mitigation strategies, providing crucial information for policy decisions and adaptation planning. Poverty reduction initiatives use data to identify vulnerable populations and allocate resources effectively, ensuring targeted interventions. Recent breakthroughs in data science have opened new frontiers in research and application. DeepMind's AlphaFold has revolutionized protein structure prediction, solving a 50-year-old challenge in biology. The deep learning system can predict a protein's 3D structure from its amino acid sequence with remarkable accuracy, accelerating drug discovery and enhancing our understanding of disease mechanisms. GPT-4 level language models have achieved remarkable advancements in natural language processing, understanding, and generation. These systems can write coherent essays, summarize complex documents, translate languages, and even generate creative content from natural language descriptions, transforming human-computer interaction. Diffusion models for image generation have created stunningly realistic images from text descriptions. Models like DALL-E, Midjourney, and Stable Diffusion have demonstrated the potential for new applications and novel possibilities for design and visual communication. Reinforcement learning from human feedback is aligning AI systems with human preferences, ensuring they behave in ways that incorporate human feedback into their decision-making processes. This approach enhances the helpfulness, harmlessness, and honesty of AI assistants while reducing harmful outputs. Netflix faced the challenge of helping subscribers discover relevant content among thousands of titles. With limited screen real estate and user attention, the company needed to maximize the likelihood that recommended content would match viewer preferences. Research showed that users typically browse for less than 90 seconds before abandoning their search. If Netflix couldn't find engaging content quickly, they risked losing engagement and eventually subscribers. Netflix developed a sophisticated recommendation system using multiple algorithms working in concert. The system analyzes viewing history, explicit ratings, and implicit feedback to tailor content suggestions. The recommendation engine employs both collaborative filtering, finding patterns among users, and content-based filtering, matching preferences to similar content. Deep learning models identify subtle patterns in viewing behavior that traditional approaches might miss. Netflix estimates that its recommendation system saves the company approximately $1 billion in annual value through improved retention and engagement. More than 80% of content watched on Netflix comes from recommendations rather than direct searches. Beyond business metrics, the system has transformed how content is created. Data-driven insights now influence production decisions, with viewer preferences informing new show development and even casting choices. Uber needed to provide accurate estimated arrival times for both riders and drivers. Inaccurate ETAs lead to poor user experience, with riders uncertain about wait times and drivers unable to plan efficiently. The system needed to account for traffic conditions, time of day, weather factors affecting travel times, and myriad other factors affecting travel times. Uber developed a sophisticated machine learning pipeline, processing millions of ETA predictions hourly. The system incorporates trip data with real-time traffic information and contextual factors. Gradient boosting machines, GBMs, capture nonlinear relationships between features, while deep learning models incorporate sequence modeling for time-dependent patterns. The engineering challenge involved adapting the model to scale to a scalable infrastructure. Uber implemented a distributed system architecture that handles feature computation, model training, and inference across multiple data centers, with rapid failover, ensuring predictions needed within milliseconds. The system achieved a 26% improvement in ETA accuracy compared to traditional routing algorithms. This accuracy improvement enhances user experiences daily, with riders receiving more reliable pickup estimates and drivers optimizing their routes efficiently. The models continuously learn from new data, adapting to changing conditions across Uber's global operations. Zillow set out to solve a challenging problem: automatically valuating homes across the entire U.S. housing market without physical inspections. The company aimed to provide accurate, data-driven estimates to help consumers make informed real estate decisions in a market traditionally characterized by information asymmetry. The Zestimate model incorporates hundreds of variables, including property attributes, location, boundaries, tax assessments, prior sales, comparable home sales, and more. The model uses machine learning algorithms to analyze these features, while the series-like modeling captures market trends. As of 2018, it covers over 100 million homes with a median error rate of approximately 5%. This algorithmic valuation has fundamentally changed how consumers approach real estate, offering accuracy comparable to property valuations conducted by industry professionals. Data science faces several common pitfalls that can undermine model performance and reliability. Data leakage occurs when information from outside the training dataset inappropriately influences model development. This creates artificially high performance in testing, but poor results in production. Improper validation involves inadequate testing of model performance on data that truly represents the deployment environment. Common issues include using non-random splits, temporal misalignment, and sampling bias. Sample bias arises when the data used for training doesn't represent the population the model will serve. This introduces systematic errors that can amplify existing inequities or lead to blind spots for underrepresented groups. Careful sampling strategies and bias audits are essential countermeasures. Correlation versus causation. Confusion misinterprets correlational relationships as causal ones. This leads to flawed decision-making when interventions are based on the assumption that changing one variable will affect another, without accounting for confounding factors or underlying mechanisms. As organizations mature in their data science capabilities, scaling from individual contributors to enterprise-wide functions requires deliberate strategies. Beyond technical considerations, successful scaling demands cultivating data literacy throughout the organization and creating career paths that retain top talent while maintaining business impact. Education and training are crucial, with initiatives like Airbnb's Data University. Approach training over 1,500 employees across departments in data skills, creating a data-fluent organization where analytics capabilities extend beyond specialized teams. Standardized data platforms, self-service analytics, and internal packages reduce duplicated effort and improve collaboration across teams. Models range from centralized teams maximizing knowledge sharing to embedded specialists, ensuring agility, to hybrid approaches that balance specialization with integration. Collaboration frameworks foster a process for cross-functional work between data scientists, engineers, product managers, and business stakeholders, while effectively translating insights into action. Open source communities have been instrumental in democratizing data science by providing freely available tools, knowledge, and collaboration opportunities. Platforms like Kaggle host competitions where data scientists solve real-world problems, with public leaderboards fostering healthy competition and knowledge sharing. Driven data focuses specifically on social impact, connecting data scientists with nonprofits and mission-driven organizations. Meanwhile, educational communities such as FastAI provide high-quality learning resources that make advanced techniques accessible to practitioners with diverse backgrounds. These collaborative ecosystems accelerate innovation and spread best practices throughout the global data science community. Automated machine learning, AutoML, represents the process of applying machine learning to real-world problems. These tools handle tasks that traditionally required significant expertise, including feature selection, algorithm choice, hyperparameter tuning, and model evaluation. The core promise of AutoML is democratizing machine learning by reducing the expertise required to build effective models. This enables domain experts without extensive data science training to leverage machine learning for their specific needs. Modern AutoML platforms provide comprehensive automation across the entire pipeline. Automated data preparation and feature engineering, algorithm selection and optimization, hyperparameter tuning using advanced search techniques, model evaluation and selection based on performance metrics, and deployment and monitoring capabilities. Organizations implementing AutoML report substantial efficiency gains, with up to 80% reduction in time required for model prototyping. This acceleration enables rapid iteration and broader exploration of potential solutions. Beyond efficiency, AutoML often produces models that outperform handcrafted ones, with standardized datasets showing results in 80% of generalized models across diverse problem domains. Transfer learning and foundation models are transforming how machine learning systems are developed and applied. Foundation models like BERT, GPT, and CLIP are initially trained on enormous, diverse datasets using self-supervised learning. This process develops general representations of language, images, or other data types without human-labeled content. GPT-4 was trained on text from the web, books, and other sources. These pre-trained models are then adapted to specific tasks with relatively small amounts of labeled data. For example, a foundational language model can be fine-tuned for sentiment analysis or summarization by adjusting weights using a fraction of the data needed for training specialized models from scratch. Advanced foundation models can perform new tasks with minimal or no labeled data by leveraging prior knowledge to generalize to unfamiliar tasks. This process is known as few-shot or zero-shot learning. These models leverage their broad knowledge to generalize to unfamiliar tasks. This capability is particularly beneficial in scenarios where labeled data is scarce or unavailable. Industries with unique requirements like healthcare, finance, and law are creating domain-specific extensions of foundation models. These adaptations incorporate specialized knowledge while maintaining the general capabilities of the foundation models to enhance performance in professional contexts. The convergence of edge computing and data science is transforming how we collect and process information from the physical world. By moving computation closer to data sources, edge computing reduces bandwidth limitations, reduces cloud processing costs, and enables new applications that require real-time intelligence. Model compression techniques such as quantization, pruning, and knowledge distillation reduce the size and computational requirements of machine learning models, allowing effective deployment on resource-constrained devices while maintaining acceptable accuracy levels. Federated learning is a distributed approach where models are trained across multiple edge devices without exchanging raw data, preserving privacy while allowing collective learning from diverse data sources. This approach is particularly useful for applications involving sensitive data. Real-time analytics at the source reduces latency for time-critical applications. Edge analytics enables immediate responses to detected events, such as predictive maintenance alerts or security notifications, without the round-trip delay of cloud processing. Smart sensors with integrated machine learning capabilities that can make autonomous decisions. These intelligent endpoints filter and analyze data locally, sending only relevant information to central systems and drastically reducing bandwidth requirements. Explainable AI, XAI, is a unified approach to explaining model outputs based on game theory concepts. SHAP values show how each feature contributes to predictions for individual instances, providing both local and global interpretability. This method supports understanding model behavior, making it a versatile tool for understanding complex models. LIME is another technique that explains individual predictions by approximating a simple, interpretable model around a specific instance. This approach helps users understand the impact of the complex model's behavior on the local region. This approach is particularly useful when understanding why specific decisions were made. Regulatory implications are significant, as the EU and AI legal systems worldwide are establishing requirements for AI transparency and accountability. These frameworks require that AI systems provide explanations for their decisions and maintain an audit trail of their actions, ensuring an essential compliance consideration. Quantum computing represents a fundamentally different computational paradigm that leverages quantum mechanical properties like superposition and entanglement. While still in early development stages, quantum systems show theoretical promise for dramatically accelerating certain data science tasks that are computationally intensive on classical hardware. Grover's search algorithm offers quadratic speedup for search problems, providing a practical way to transform database operations and feature selection, while quantum machine learning algorithms offer potential speedups for classification and clustering tasks. Current systems are limited by noise and stability issues. Hybrid classical quantum approaches are being explored to mitigate these challenges. Quantum optimization problems leverage complex optimization challenges more efficiently, providing new avenues for solving problems in logistics, finance, and supply chain management. Though current systems are limited by noise and stability issues, hybrid classical quantum approaches are being explored to mitigate these challenges. Becoming an effective data scientist requires developing a multifaceted skill set that combines technical expertise with business acumen. The foundation begins with strong mathematical knowledge, particularly in statistics and linear algebra, which provide the theoretical underpinnings for most data science techniques. Programming skills in languages like Python, R, and SQL enable practical implementation, while data analysis and visualization capabilities transform data into insights. Domain expertise provides essential context for applying these technical skills to real-world problems. At the highest level, Business communication skills ensure that complex findings can be translated into actionable insights that drive decision-making. Effective communication bridges the gap between technical and business stakeholders, ensuring that data-driven strategies align with organizational goals. The data science field offers diverse career trajectories to match different interests and strengths. Many professionals begin in data analysis, focusing on descriptive analytics and trend modeling before progressing to more advanced roles. Data scientists combine strong analytical foundations with engineering skills, while machine learning engineers specialize in applying and scaling algorithms in production environments. Data engineers focus on building the infrastructure that enables analytical at scale, creating and maintaining data pipelines and databases. For those with leadership ambitions, management tracks lead to roles like Analytics Director or Chief Data Officer, where strategic vision and organizational leadership are key. Salaries in these roles vary widely, with entry-level positions ranging from $80,000 to $100,000, while leadership roles can exceed $200,000 depending on the title and experience level. Data science career paths offer opportunities for growth and advancement, with roles that cater to both technical and managerial aspirations. Learning resources and communities play a crucial role in supporting data science education and professional development. Online courses on platforms like Apex Virtual Education, Coursera, edX, and DataCamp offer structured learning paths from foundational concepts to specialized programs like the Google Data Analytics Certificate that provide job-ready skills. Books and documentation, such as The Elements of Statistical Learning and Python for Data Analysis, offer essential reference material for working practitioners. Community engagement through online forums like Stack Overflow and Reddit's r/r Data Science create opportunities to learn from peers, solve real problems, and build a professional network. These communities provide mentorship and support for newcomers to the field. Practice projects, including open-source contributions, competitions, and self-guided projects, offer practical application of theoretical knowledge. These experiences demonstrate skills to potential employers more effectively than certifications alone. Data science has evolved from a specialized technical field to a cornerstone of digital transformation across industries. Organizations that effectively leverage data enjoy significant competitive advantages. 85% of data-mature companies report substantial business benefits, including increased revenue, reduced costs, and improved customer experiences. As we look to the future, the democratization of data science tools will empower more individuals to contribute to this field, while advances in automation will shift focus from routine tasks to strategic innovation. The most successful data professionals will combine technical expertise with domain knowledge and continuous learning, adapting to an evolving landscape where the only constant is change itself.